So please feel free to interrupt at any moment with comments, questions, concerns, etc. I'll talk about a paper that appeared yesterday. So far, nobody found a mistake, so I'm happy to talk about it. With Yiqiu, Han, Xiaoyang, Huang, Andy Lucas, Fyodor Popov, and myself. It's a paper in a mix of fields. I think it's quite appropriate for the school. It has some quantum entanglement stuff, some statistical mechanics stuff, and quantum field theory, and even ADS-CFT. So let me explain the topic kind of philosophically for 5 to 10 minutes, and then I'll show you the mathematics and some of the things that we actually did. So what is the general philosophy? So as you know, when we are at finite temperature, we need to minimize the free energy rather than the energy. So the free energy is given by the energy minus the temperature times the entropy. And now if you go through like basic courses on thermodynamics or statistical mechanics, people will tell you that at high temperatures, so this is the usual logic, at high temperatures, therefore, we need to minimize the second term rather than the first term. The first term is not important. That's just the qualitative arguments. So we need to maximize the entropy so that the second term is as negative as possible. We need to maximize the entropy. And then we have an intuitive idea of what it means to maximize entropy. Entropy for us is a measure of disorder, of how many bits of information need to be conveyed to specify the microstate. So if an alphabet has only one letter, this alphabet carries no entropy because any string of letters that you send carries no new information. If an alphabet has 1,000,000 letters, it has a lot of entropy because any new string of letters carries a lot of information that you didn't know before. So then we have this intuitive idea that maximizing entropy, meaning that we're looking at states which are completely disordered. So very disordered states. And these disordered states are just linguistically, it means not ordered. So very messy states with no order. Okay, and then the next implication is therefore that any order, whether it's topological order, superconductivity, magnetic order like ferromagnetic order, Ising type order, any order disappears at high temperature. So order disappears at high temperatures. And of course, this is what we see in nature, right? So this logic is very powerful conceptually because that's what we see in nature. Indeed, solids in nature, as you heat up solids, they turn into liquids. Why are liquids more disordered than solids? Because solids have a lattice structure, and the lattice is a very ordered structure, while liquids are just messy and they have no visible structure. Ferromagnets lose their magnetism and they fall off the fridge, so they become paramagnets. So in ferromagnets, the spins are all ordered in the same direction, and this property is, of course, lost when you heat them up. And of course, the same can be said about topological order. So topological order is a quantum phase. These are classical phases. Topological order is a quantum phase with a lot of entanglement in the ground state. Maybe you heard about it due to the theme of the school. But of course, topological order disappears, and you get no entanglement at high temperature. And there's a technical name for that. It's called entanglement death. It's a mathematical theorem that all the entanglement dies at high temperatures, and I'll explain what it means in formulas. So these are all like instantiations of the same thing, of the same general logic. Now, this logic also has an interesting implication for ADS-CFT. So I'll just explain what it means for high energy physics. So at least for holographic theories, the high temperature phase of a holographic theory is dual to a black hole. So in ADS-CFT, we have a nice geometric description for the high temperature phase of a strongly coupled holographic quantum field theory, and that's a black hole. So the black hole is dual to quantum field theory at high temperatures. Okay? And what does it mean for the black hole, for the high temperature phase of quantum field theory to be disordered, meaning that there is no order? It means something very nice in gravitational physics. It means that the black hole has no hair. So no hair. What is hair? Hair is some expectation value of a scalar field near the black hole horizon. And we believe that we don't need to specify the expectation values of scalar fields near black holes. And if there was order in quantum field theory, then we would need to specify the expectation values of some fields. So this is dual to those qualitative theorems. No order. So actually, I started working on the subject trying to prove the no-hair theorem. But what ended happening is that we found lots of counterexamples that were not known. Okay, so the no-hair theorem is dual to what I'm saying. Okay, so this is the qualitative picture. And now I'll show you more technically what all of this means and whether it's actually correct. Whether these expectations are actually correct. Okay? Yeah.
So at finite n, you can
I could hear. It's okay. Okay. Sorry. Yeah.
At finite n, you can develop such expectation value, right? Those hairs. In the large.
I didn't really. I don't mean that this is like infinite n. I'm talking about ADS-CFT in the strong form, which is, like you take some very large finite n. At very large finite n, a black hole is dual to that, and this is dual to that. Let's say n equals 100. I don't want to discuss the artifacts of some limits. Let's say n is just large and finite, then yeah.
Is this no-hair theorem valid at high temperature only or at all temperatures?
Which no-go theorem?
No-hair theorem.
Well, no, I'm saying the no-hair theorem is dual to the statement that there is no order at, thank you, maybe that's what you meant. There is no order at high temperature.
Okay.
Okay, so because this is no-hair theorem for large ADS black holes, the black holes that are dual to QFT at high temperature, they're called in the literature large ADS black holes, because you might know that there are also small ADS black holes. There are two kinds of black holes. So the no-hair theorem here applies to those, allegedly.
Not to the small.
Not to the small black holes. Okay, so that was my actually original motivation. But by now we know. I'll show you that it's actually not. It's actually not true. There are counterexamples which are very interesting counterexamples in statistical mechanics. Okay. So let me try to explain a little bit more mathematically why this expectation exists. So for the sake of a pedagogical discussion, you can think about a system that's completely finite, so we don't have to deal with the fact that in quantum field theory we have a degree of freedom at every point in space. So think about some theory that lives on a regularized lattice, let's say in two spatial dimensions. And you can think about either a quantum system or a classical system. So each site, let's say, has either a classical variable, which can take some classical numbers, classical values like 0, 1, 2, or it could be a quantum spin or something. Okay? So if it's a classical system, we use the Gibbs distribution, right? Or the Boltzmann distribution. So we just have some configuration space, and we say that the probability of every configuration is given by this real number, well, positive number, which we interpret as probability. And then we say that as the temperature increases, namely as beta goes to 0, this probability distribution becomes 1 over z, okay? So I'm just putting beta equals 0 in the numerator. And this is also known as uniform distribution, right? It's like a completely uniform distribution over the space of possible microstates. And so this is called uniform. And now you can easily understand if there is a uniform distribution over the space of microstates, it's very clear that, at least for local, it's very clear that this site cannot talk to this site because the distribution is completely uniform. There cannot be any correlations by definition. In the uniform distribution, there are no correlations. And therefore, the expectation value of any two operators at points x1 and x2, just factorize. That's at very high temperatures. And therefore, there cannot be order. Order just means that all the spins are aligned or all the degrees of freedom are aligned. And this is just, so if you take the beta going to 0 limit, this is true. Just from the fact that you have a uniform distribution over the space of states. And therefore, there cannot be any order. So, in fact, mathematicians, I think Dubrovshin was the first one, managed to prove rigorous theorems that go along the following lines. So if you take any beta that's smaller than beta critical, so these people proved that there is a critical temperature above which this is true at separated points. So they proved that O1 x2 just factorizes if x1 minus x2 is very, very large. Okay. So people actually proved mathematically rigorously under some assumptions that there is factorization at high temperatures. The distribution is essentially uniform up to exponentially small corrections. And therefore, there is no order, there is no correlations. When you see such things, of course, you have to be somewhat suspicious. These are mathematical theorems, and they have assumptions. So we'll explore some of the assumptions. And there is an analog in quantum mechanics. In quantum mechanics, the story goes almost along the same lines. In quantum mechanics, we just replace many of the formulas on that side of the board by quantum operators. So in quantum mechanics, we use a density matrix, right? So H is an operator, and we have a density matrix. You've probably seen that already a couple of times from various lectures here. And you can say the same things, that when beta goes to 0, this becomes the unit density matrix, which is called the maximally, sometimes people call it, instead of uniform, they call it the maximally mixed density matrix, or the thermal density matrix. And then you can prove the same things. So there are papers, you can find them in this reference, which proved rigorously that at high enough temperatures, there is no correlations. And they even proved something stronger, which is that there is no entanglement. So that means that people proved that if beta is smaller than some beta c, under some assumptions, this matrix rho, which is the density matrix, actually can be decomposed as a product of density matrices over subregions A and B. And this maybe is not very intuitive, but that's what's called the separable density matrix. And it essentially means that there is no entanglement between A and B. So the full density matrix is just a product of density matrices in A and B, and they're unentangled. There is no entanglement between A and B. So that's a mathematically rigorous result at high temperatures. And that's called entanglement death. So that's what people call, that's what people in quantum information theory call entanglement death. Okay, so to the extent that we understand mathematically why magnets don't exist at high temperatures, or quantum magnets don't exist at high temperatures, or they become trivial, these are the underlying theorems. These theorems have some assumptions. Yeah. I couldn't really hear.
So you said for quantum system, this density matrix at very high temperatures looks like a separable state.
Yes,
But
separable
why should
state.
not why should even the classical correlations die out?
Oh, this is true for any A and B. Any A and B that together make up the full system. So that means that there is no entanglement between any two subregions.
But there seems to be some classical correlations.
There is no classical correlations either.
Oh, I see.
There is no quantum correlations and there are no classical correlations.
Okay, I thought you are writing, because you are writing the sum over I, rho tensor, rho I tensor rho I.
Yeah, but, well, if you actually compute the expectation values of local operators in that state, you will find that they factorize.
Okay.
So sometimes this product, okay, that would still be true in that separable density matrix. Yeah.
Yeah, a quick question also. Have people looked potentially at sort of microcanonical definitions of thermal states? Again, for generic situations, the microcanonical expectation values still look similar to the canonical ones. But do you know of any theorems?
Yeah, that's a good question. I think there are scars that theorems might involve like additional assumptions like genericity, because it's known that there are, I think even in chaotic quantum systems, there are scar states at high energies. So I think, yeah, well, I'm just going to focus on this ensemble to avoid maybe having to make assumptions about the genericity of states. These are like very clean, and you can find many of these theorems in the book of Barry Simon on lattice gases, both quantum and classical. This is also called uniqueness of the Gibbs measure. That's if you want to look it up on Wikipedia. It says that at very small beta, this actually is unique in the sense that it's like the uniform distribution up to exponentially small corrections. And it's called Dubrovshin theorem. Okay. Now let's talk about what goes, is it really, what goes into these theorems. So one important thing that I want to show you today is the importance of this word. And we'll discuss it both in the quantum and classical mechanics. So maybe in high school you encountered some confusing puzzles about slicing pizzas with uniformly distributed lines. This is a very famous puzzle of Euler. But it kind of showed that uniform distributions don't exist. If you have, let's say, uniform distribution over the space of lines doesn't exist. A uniform distribution over the space of integers doesn't exist. Okay? There is no such thing as a uniformly distributed integer number. Is that clear? The moments of this distribution don't exist and so on. So we're going to try to explore what happens when the uniform distribution doesn't exist. Now, what happens when the uniform distribution doesn't exist? So one case where it doesn't exist for sure is quantum field theory. In quantum field theory, because we have a degree of freedom at every point in space, there is no such thing as uniform distribution. And if you follow the recent discussions of von Neumann entropies, the terminology is that the unit distribution is not trace class. There is just no such density matrix in quantum field theory. So in quantum field theory, there is no such thing as the unit density. In quantum field theory, the density matrix which is proportional to 1 doesn't even make sense, doesn't exist. And mathematicians would say it's not trace class. It's like a sophisticated way, I think, of saying that it doesn't exist. Another situation, which is a toy model that we'll explore where it doesn't exist, is just in the classical statistical mechanics. So let's discuss statistical mechanics, where we can understand everything and even put it on the computer, on a lattice. But we will allow to slightly deviate from the usual paradigm where the degree of freedom on each site is 0 or 1, like Ising type. And let's say U is a site. U will label sites. So we will allow for each site to have a degree of freedom which is an integer. And let's see what happens. So it's a boson. Now, it's a very physical construction. It's just that you have a lattice, and bosons can come to the lattice from some reservoir. There is some reservoir of bosons, of photons, let's say, and they can come visit the lattice. They can sit on lattice sites, and the number of bosons on each lattice site could be 0, 1, 2, 17. Okay? On this configuration space, there is no uniform distribution. Is that clear? So we'll just explore some models in this class, and they're still very physical. You can simulate them. You can probably cook them up experimentally. I'll show you that these models already lead to violations of the intuition in some cases. Okay, so let's explore these models. Let's write an energy function, namely a Hamiltonian. So there will be, I'll just write the first term. There will be two terms, two coupling constants. Well, actually only one. So the first term.
Sorry.
Yeah.
Can I make a question? What would it mean, for example, in the example of the grid, for there to be a uniform distribution?
Let's say in the Ising case. So in Ising we have a grid, but on each site we have a number that's either 0 or 1. Okay, so if the grid is finite, let's say L by L, there is a uniform distribution on that space, because in total there are 2 to the L states, 2 to the L squared, I meant, 2 to the L squared states, and there is a uniform distribution on that space of states. It exists mathematically, because it's normalizable. It's a discrete combinatorics thing. But here there is no such thing as a uniform distribution. So the first term with positive mu, okay? The first term is very simple. It just says that you have to pay some price for bosons to come to the lattice. So every time a boson comes to a lattice site, you just pay energy mu. And that's it. It's just a chemical potential. And the second term will be a repulsion between nearby sites. So this symbol means that U and V, the sites U and V are adjacent. This lattice is a bipartite. Let me just make it clear that it's a bipartite lattice. So we can mark it like a chessboard, okay? So that there are so that there are axes and there are circles. And okay, so this is a bipartite lattice. And if a particle sits on a circle, then you'll have to pay a lot of energy for a particle to sit on a cross, and vice versa. So it's just a simple repulsion term between the two bipartite lattices. So I'll take it to be something like nu squared nv squared. Actually, it's not important that it's squared. The conclusions work even if it's a different power. But I'll just put it squared because that's the simplest case to explain. Okay, is the model clear? So photons can come to the lattice, they sit on lattice sites, and they repel each other. So a photon on a white circle repels photons on a cross circle, on a cross site. Okay, yeah. Yeah. And you.
Yeah. Is the sum over all lattices or nearest neighbors?
This
The interaction is
symbol-
short range or long range?
This symbol means nearest neighbors.
Nearest neighbors, okay.
So UV means that they're nearby.
Okay, good.
I don't count diagonal, non-diagonal, only one connection. Okay? Yeah.
Just a quick thing, should we think of the lattice as being finite sized?
You can think about it as L by L, but eventually we want to take a thermodynamic limit. Just to discuss phases of matter, we take thermodynamic limit, no?
Yes, but so what are the boundary conditions on this thing?
I'll tell you everything about it. For now, think about it as L by L with periodic boundary conditions. L by L, you can put it on the computer with periodic boundary conditions. Okay.
Is it essential for this construction that this lattice label n goes up to infinity, or can I also, can I think of this as bounded, or?
This?
Yeah.
I'll discuss it at the end. If it was bounded, then the theorems would apply because there would have been a uniform distribution.
Okay.
But you still get something from it. I'll tell you at the end, maybe. Just one, yeah.
So a small add-on to that. So you said that we're interested in taking the thermodynamic limit at the end, but isn't this model equivalent to, for example, taking an icing model and then just doing a coarse graining of L by L blocks and counting the number of one states in the full block and then taking the limit of those blocks to infinity?
I definitely don't think so. As you will see, this model behaves differently from everything you've ever seen.
Okay.
So I don't think it's equivalent to
But
icing. It
classically-
definitely is not equivalent to icing.
No, not to icing, but let's say I take icing on an infinite lattice, I cut that into n by n blocks, or L by L blocks.
No, I
and
understand what
count
you're
the
saying.
degrees of freedom in the block.
I understand what you're saying, but for some reason the answer is no.
Okay.
I think okay, let me not say more than that for now. We can try to discuss it more later. Okay, so let's analyze the phases. We just do e to the minus beta h. When beta is huge, when beta is larger than anything, this is the low temperature phase, and we have to be near the ground state. And anybody wants to suggest what's the ground state? What's the lowest energy configuration? No, yeah. So the ground state is no bosons, just n equals to 0. But when you turn on a small temperature, of course, bosons could sometimes come visit. So the probability for having a boson on some lattice site is e to the minus beta, and beta is huge, so sometimes some bosons come to visit. The probability that they will be on adjacent sites is minuscule, and so essentially you can drop this term. This term is not important. And this is called gas. This is a gas. You can call it gas, liquid, whatever. Liquid and gas is the same thing. You can call it a gas phase. So this model is a gas at low temperatures. Okay, that's not shocking. There are many systems like that. Now let's discuss beta smaller than anything. And this is where it gets very interesting and less trivial. Okay? So what happens when beta is very, very tiny? We have to explore the states which have the most entropy, right? Because F is e to the minus ts. And we have to understand what states have a huge amount of entropy. So a reasonable guess from statistical mechanics is that it's a liquid state. So there are particles everywhere on the lattice. There is some average number n of particles. So I'm going to tell you something like a mean field analysis. So if you were to guess that it's a gas phase, you would say that there is some average density. So there is some average number n bar of particles everywhere on the lattice. And it doesn't see the bipartite structure. And the number n can fluctuate from site to site. So there are fluctuations of the number of particles at each site. But there is some good average n bar. And you have to count how many states are there at some given energy of that sort, where there is a more or less uniform distribution. I'll just write the answer now, and I can try to show you the derivation. So exponential of the entropy is the number of states. So the number of states which are gas type goes like the temperature to the power L squared over 2. L squared over 4. This is the number of particles. This is the number of, at temperature T, this is the number of states that you will see. This is the number of accessible states at temperature T. It's the temperature to the power L squared over 4, where L is the size of the lattice. So it's a lattice L by L. Okay, so this is the gas phase. Another interesting phase that we have to examine is a solid. We usually don't discuss solids at high temperature. They're supposed to melt. But let's discuss the solid phase. Here, the solid phase is where particles only occupy one of the bipart lattices. So let's say we only put particles, sorry, that would be very bad notation. Let's say we only put particles on the crosses, but we don't put any particles, almost, on the circles. And let's count how many states are there of that sort. So the solid is that we put particles on the crosses, but probabilistically, almost never on circles. If we put particles on crosses, it actually we can actually gain something, bizarrely enough. By forming a solid, we can gain a huge amount of entropy. Let me show you why. It's because if you put particles on the crosses only, this term wouldn't matter. And the number of states up to energy E would be determined by the first term. So if you do the counting, which I'll do for you soon, you'll find that it's temperature to the power L squared over 2. So there are many more solid microstates than gas microstates. And therefore, when the temperature is high, this model is a solid. So this is a very strange phase diagram where at low temperatures you have a gas, you heat it up, it becomes a solid. And it happens due to entropy, and the solid breaks Z2 symmetry. So the solid is an ordered phase because it breaks the Z2 symmetry to nothing. The Z2 symmetry is the translation by one lattice site because we have to occupy by one of the sub-lattices. Okay? So this is the idea, and now I'm going to explain why it's true, how to do this counting. And are there any questions about the bottom line? Yeah.
We need to the minus beta mu over there.
Hmm?
The probability for the gas phase when the temperature
Oh,
is
yeah. I'm sorry. I forgot to put mu. Mu is 1.
Thank you. And how do the dimensions work out over there? I mean, what is the temperature scale width here?
Yeah, you have to divide it by mu or something. I'm not going to even write it. Okay. Okay, so why does this happen? So usually, ordered states have lower entropy than disordered states because ordered states carry you don't need to send bits to explain how they look like. You know how a solid looks like by just looking at a small patch of it. So ordered states usually have solid states have a very low entropy because they have very structured states. But here we see the main idea, which is sometimes, so that will be a thing that we'll see. Sometimes the following thing happens. Ordering in 1 degree of freedom opens up, in quotation marks, opens up many possibilities for other degrees of freedom. So we see that sometimes ordering actually does buy you a lot of microstates because once you have an ordered states for some degrees of freedom, the other degrees of freedom are much more free to fluctuate. So in the liquid phase here, you don't form a solid, so you gain a little bit from that, but you lose a lot because of the interactions. While in the solid state, you occupy one sublattice and then the interactions don't punish you, and the bosons are much more free to fluctuate. So we see that sometimes ordered states are actually the typical states, and they carry the highest entropy. And the phase diagram of this model is the following. So this is the temperature. We have a gas at low temperatures. Then we have a solid at high temperatures. And numerically, we think that this is a second order. We did some Monte Carlo simulation, and we saw a second order transition here up to numerical errors. Okay? So what I want to do now is to show you how to count the states. Just how to count the states approximately. And then we'll move on to quantum field theory to show that the same things can happen in quantum field theory. But the main idea is this. So if you understand that, then you've understood the message of this lecture. That sometimes ordered states are actually typical. And we'll then use the same trick to push superconductivity to high temperatures, push superfluidity to high temperatures, and many other things. Now, are these models physical? Probably. There is nothing that seems unphysical about them. So, okay, now I'll show you how to do these estimates. Okay, so let's estimate, let me show you how to estimate the entropy of the checkerboard, the solid state. So we call the solid state the checkerboard state because we only occupy, let's say, the black or white sides. So I'm gonna try to now show you how to do this. So let's suppose that we occupy only the crosses. Then we can essentially ignore the second term in the Hamiltonian, and we just need to discuss this one because the second term is unimportant. So we have to calculate, let's say we fix some energy E as a cutoff. We have to calculate how many microstates are there, up to energy E on the checkerboard. Okay, so let's instead of talking about the full energy, let's talk about the energy density, epsilon, because it's a very translationally invariant state on macroscopic scales, okay? So, so here we see that there are epsilon states from each side. And so the answer is epsilon times L to the power L squared over 2. So that's essentially because there are epsilon states from each side of the checkerboard. And the exponent is L squared over 2 because there are L squared over 2 sides on an L by L lattice which are occupied in the checkerboard pattern. Okay? So that's trivial. Okay, so let's do now the other one, which is liquid, or the gas phase. Here, it's a little bit more complicated. We have to assume that there is some uniform distribution n bar of particles to first approximation. So we have some uniform, so the number of particles is some average n bar plus fluctuations. And at temperature T, the energy density is some epsilon which is proportional to T. This term dominates because we imagine that there are more and more bosons coming to visit the lattice. So this grows like the number of particles to the 4th power on adjacent sites. So we can estimate that the number of particles on average goes like the temperature to a power a quarter. Is that clear? And that allows us to count how many states are there. Because now we just take that, we raise it to the power L squared, so we get T to the power L squared over 4. And T is the same as the energy density. The energy density is of order of temperature. And that's it. This is a mean field analysis. You can say, oh, it's wrong because I ignored the fluctuations in the density of the liquid or the gas. So at the end, we did a Monte Carlo simulation, and it actually vindicated this argument. It is true. That's how it scales to leading order. There are corrections, but at very high temperature, that's how it scales, or at very high energy density. So clearly, you see that in this model, the ordered phase has a higher entropy. There are just more microstates that are ordered. And okay, so this is the essence of this example. And now I'll move to quantum field theory. Are there any questions about it?
Yeah. So why do you say that the gas does not break translations? Don't we have sound waves in the gas because of that?
So we have sound, you said?
Sound waves.
Yeah,
when I have a gas, I think of it as something that breaks translation. Why?
No, a gas by definition does not break translations. Solids break translations because solids have a unit cell. It's a crystal structure. Gas has more or less uniform density. If you were to measure the density in the room, you'll find that it's uniform up to exponentially small, up to very small corrections. A sound wave is an excitation on top of the ground state of the gas.
But I think of it as the Goldstone boson associated to the breakdown of translation
No, it's a
symmetry.
Goldstone boson that's associated to the breaking of boost. It's very important. A gas breaks boost symmetry by virtue of having constant density. It does not break translations. So the Goldstone bosons in hydrodynamics are due to the spontaneous breaking of boost. And the Navier-Stokes equation follows from boost symmetry. That's why you get velocity. That's why the velocity is like the fundamental variable in the hydrodynamics. While in solids, the fundamental variable is a phonon because it comes from breaking translational symmetry. Okay? So gases don't break any symmetries on the lattice. They break a symmetry in the continuum, which is boost. But on the lattice, gases don't break any symmetry. Okay, any other questions? Good. So this is the essence of this example. Now I'll tell you a little bit about quantum field theory. So quantum field theory. In quantum field theory, the space of states anyway does not admit a uniform distribution, as I said already a couple of times. But that doesn't mean that any quantum field theory that you'll study has a weird phase diagram. It's actually quite the opposite. It's extremely difficult to find quantum field theories which have a non-standard phase diagram. Okay? So I'll show you one class of examples now that we found. I should say that here I'm not talking about classical temperature anymore. I'm talking about I'm going to talk about quantum field theory in d+1 space-time dimensions. And instead of doing calculations in the vacuum, we're going to do calculations in the density matrix e to the minus beta h over z. Okay, so we're talking about now quantum temperature. The previous discussion was classical temperature. So now it's going to be quantum temperature. And I'm going to tell you about a class of examples which are pretty simple without gauge fields, just scalar field theories that were found. So just as a warm-up, this is a warm-up. This example doesn't work, so to speak. It behaves like you would expect a reasonable system to behave, but it's a good warm-up. So you study the following action. I'm separating time and space just because I want to emphasize that I'm talking about quantum temperature now. And I'm doing calculations in this ensemble, not classical temperature. So let me just remind you what happens when you study the quantum field theory of a scalar field, which is arranged into some vector. It has isospin, and we look at this model, a scalar field with quartic interactions, and phi is 1 to n. This is called the Wilson-Fisher quantum field theory. This is the Wilson-Fisher. This is the Wilson-Fisher model. They wrote a very famous paper 50 years ago showing that it can be analytically discussed when d is very close to 3. So 2.99 space dimensions. They found this epsilon expansion, and they were able to solve for the infrared limit of this model. We now know much more about it. It's a conformal field theory in the infrared. It's a conformal field theory in the infrared. You can deform it. You can deform it by ending m squared phi squared. There is a symmetry broken phase and a symmetry unbroken phase. So I'll draw it now on the board. We can add a deformation to this model. I'll just write it here in parentheses. It's just to guide the eye. You can add the mass squared. If this mass squared, yeah. Oh, sorry, yes, of course. Squared. Yeah, it's a square. Yes. Any other questions? So this is, what does this model do? At 0 temperature, namely in the vacuum, as a function of m squared, it has the following phase diagram. So here it's gapped. You see the bosons are just massive and the infrared is empty. Infrared is gapped. While if m squared is negative, you get symmetry breaking of SON symmetry, of ON symmetry, broken to ON minus 1. And this leads to Goldstone bosons. So this is Goldstone bosons, which describe, and this phase is called in condensed matter a ferromagnet. This is the phase where you have magnetic order, because you have Goldstone bosons and the spins are pointing in the same direction in the ground state. Okay? So this is the usual story about this model. And now you can add another axis to this diagram, which is the temperature, where instead of doing calculations in the vacuum, you do calculations in the density matrix e to the minus beta h. And you can ask, what does this model do? And what turns out is that this is a phase transition between the ferromagnetic and gapped phase. This phase transition is second order, and 50 years of bootstrap and conformal field theory has gone into determining the critical exponents at this phase transition. You probably heard about bootstrap and scaling exponents. But a more not interesting, but a more pertinent question for today is what happens when we crank up the temperature. And what happens is this. So the line of the phase transition turns left rather than turning right. And that's crucial, because it means that this is the magnet phase. This is the phase where the magnet doesn't fall off the fridge. And this is a disordered phase. So if you start from here and you crank the temperature up, you'll eventually make the magnet fall off the fridge. And you can ask, why does this line turn left? Why didn't this line turn right? It seems like 50-50. But of course, any sensible person would tell you that it always has to turn left, because otherwise magnets would not disappear. And it's extremely difficult to find an example where the line goes the other way. That's basically like a counterexample to no-hair theorem, if you want. It's a version of the statistical mechanics model that I showed you, where the line went the other way. So a couple of years ago, I just started looking for QFTs where the line would go the other way. It seems like 50-50, but it's really not 50-50. It's extremely difficult to find an example. So one example now was found, and it was confirmed by Monte Carlo, and it was confirmed by some functional renormalization group. So we believe we now have an example of a fully renormalizable, stable quantum field theory with this property. I'm going to show you the example now, okay? That shows that, indeed, there is no theorem in quantum field theory either. There are counterexamples. So let me show you the example. It's a variant of this Wilson-Fisher theory. So the action is slightly more complicated than the Wilson-Fisher model. And this example was found together with Chang-Ha Choi, Smolkin, Rabinovici, and Chowdhury. And later, this example had some difficulties with doing some 1/n expansion and perturbation theory. So lately, there was also a very important contribution by Popov, who managed to nail it down completely, doing some additional 1/n expansion. And there is, in parallel, a lot of numerical work on this example that you can find in the references of that paper. So this example seems to really work, and it's a fully legal quantum field theory. So the first terms are identical to the Wilson-Fisher model. The first terms are identical to Wilson-Fisher, but let me just write it like that. This is the classical Lagrangian. what is the cast of characters? The cast of characters is a scalar field which is like in the Wilson-Fisher case, has n components. But there is another scalar field psi, which is real, and it has a Z2 symmetry. And this Z2 symmetry is going to be the main actor, the main character. So this is the model. This model has some things that must be said about it, because it can raise some questions. In statistical mechanics, we were told that we should call this model biconical. I really don't know why. I've asked many people. But we are told that this must be called biconical model. The symmetry group of this model is ON times Z2. Okay? I think there is some, okay, that's probably irrelevant. So this is the model. Now, classically, this model has many ground states. The potential is bounded from below, clearly. The potential is like plus, but there are many ground states in this model classically. These are when phi squared is equal to psi squared. So there is like a manifold, if you want, of ground states. Quantum mechanically, due to some degeneration, the effective potential of Coleman-Weinberg, this is lifted. So this is lifted quantum mechanically. And there is a unique ground state at the origin. So there is a unique ground state. There is a unique ground state when phi is equal to psi is equal to 0. This is the 0 temperature ground state. And this is a conformal field theory. You can add various perturbations, such as m squared psi squared, which I can write in parentheses. You can add m squared phi squared, and so on. This model has many relevant perturbations. Actually, I think 3, unlike the original Wilson-Fisher model. So it's a conformal field theory that describes phase transition between many phases. There is a magnet phase. There is a phase with a condensate for psi, but there is some conformal field theory at the locus. Yeah. Yeah.
Are you assuming d less than 3 to every
Okay, yeah, I hope
relevant
nobody would,
operators?
I hope nobody would, but yeah, if d is exactly 2, which is the most interesting case physically, there is another term that you have to add because it can be generated by perturbation theory. So actually, when we do the analysis, we do take that into account, and that's why the calculations are really horrendous. But they are now completed. I'll just erase that because I don't want to having to mention. If you are above 2 dimensions but below 3 dimensions, you don't need to worry about 6. But then you're in fractional dimensions, and it's not a very interesting thing to do. So the interesting case where it's an actual quantum magnet is d equals 2. And then you have to add the sextic interaction. Okay? Any other good remarks or bad remarks? Okay, so in this model, I'll just now write the phase diagram. In this model, there are many coupling constants. There is m squared phi squared, m psi squared. I cannot draw a phase diagram in all the directions, so I'll just do it crudely. I'll just call the coupling G. G is schematically some combination of these masses because I cannot draw a multi-dimensional phase diagram on the board. So there is this biconical conformal field theory. And then there is some ordered phase. Let's say psi condenses or phi condenses or both. And then there is a disordered phase. Okay, so the diagram is very similar to before. This is the coupling constant G. And then you can try to calculate in the density matrix e to the minus beta h. And it turns out that in this model, the line goes the other way. Yeah. Yeah, it's some combination of these terms. Because you need to draw a multi-dimensional phase diagram. So the question was, what is G? G is just some label for some relevant perturbations. You see in this model, it was very clear what it was. It was just m squared. There was only one interesting perturbation. But here I have two interesting perturbations, and I cannot really draw a multi-dimensional phase diagram, so I just draw it schematically. Okay?
So it's a combination of the phi square mass and the psi mass.
Yes, it's some combination of those, whatever you want.
Of these
Yeah.
two relevant perturbations.
Yeah. And in this model, it turns out that it turns the other way. Okay, that's what an explicit calculation shows. And the order here is a non-zero expectation value for psi.
So,
So-
if one were to define some other combination, is it possible that for generic relevant perturbations, it will still go the expected way?
No, so the amazing thing is that this is not fine-tuned.
I see.
For any relevant perturbation, the high temperature phase is always ordered for the psi variable. So the high temperature phase always has Z2 hair, so to speak. It always has a Z2 hair. Okay?
Thank you.
Yeah, so it's not fine-tuned, it's completely generic, and that's what it does.
How about this ON symmetries?
The ON is unbroken. There is a theorem that continuous symmetries at finite temperature cannot break in 2+1 dimensions. So it's kind of guaranteed to be the correct answer. Any other questions? Okay, now the calculations in this model is strongly coupled, so calculations are hindered by our lack of analytic control over such models. So what is done in practice to prove this statement is a 1/n expansion. But numerical simulations and also some estimates using the 1/n expansion suggest that this is true at least for n bigger than 10 and maybe even n bigger than 3. These are two estimates in the literature. So for certain, it seems possible that some quantum fields are ordered at arbitrarily high temperature because some other fields can fluctuate more freely, exactly like in our lattice gas model at the beginning. So this mechanism seems to be possible in quantum field theory as well. Yeah. Yes. Oh yeah, we were waiting for the microphone.
So what would you say is special about this action? Because it looks pretty close to the other
Yeah,
one.
it's
and
very
it has
close
like this
to-
very special behavior. And it doesn't seem to be too
Yeah,
too
I think one
complicated.
thing you could say is that ordering psi kind of makes phi, so the field's fine, the Wilson-Fisher model, as you crank up the mass, as you crank up the temperature, they have less and less possible fluctuations because of the bi-screening. Here you could say that qualitatively, when psi condenses, that the bi-screening length becomes bigger and they can fluctuate more freely. So this minus sign is crucial. You see, if I put a plus sign, this would be just the ON+1 model. Guess what? It just joins the other ones. But the minus sign is crucial. Still, it's not fine-tuned. As soon as you do that, in a small neighborhood of the fixed point, it's always ordered at high temperature. Yeah. Well, here's some extra work.
Sorry to. So I don't understand why you say that it's not fine-tuned, because the quartic coupling are relevant. There are 3 of them, so you are picking up a specific combination.
Yeah.
So why do you say that it's not
No, I'm
tuned?
just saying that what we do is a calculation of the conformal field theory, which tells us which way the line is turning. And as soon as you found that the line is turning this way, it means that it doesn't matter where you start at 0 temperature. When you go to high enough temperature, you're always in an ordered phase. So it's a local picture in the vicinity of the fixed point. That's why it's not fine-tuned.
So you are saying that you would expect the same behavior if you detune that coupling and you introduce
Yeah,
more
and it
couplings.
also makes physical sense, because at very high temperature, who cares about the relevant perturbations? So as soon as you found that this is the answer at the fixed point, you're done. It's guaranteed not to be fine-tuned. So now I've shown you that it's possible in lattice models and quantum field theory models. And now I'll show you how it's possible for superconductivity. Yeah.
Is there a tuning in which the line does not go left, right, but straight up?
But stays up?
Straight up.
Straight up.
Like, yeah.
Yeah, I don't know.
Maybe the phase between this phi square and minus psi square, if it's like I times, it's in between the two. Something
Yeah,
like
yeah.
that. Can I say that?
I don't know.
Okay.
Okay. Let's keep going now for the last 10 minutes. Unless there are more questions, I can rush through the superconductivity example, or we can discuss these examples more. I only have 10 minutes. So maybe I'll just say in one sentence, the superconductivity model uses the same idea. In superconductivity, we form Cooper pairs between electrons of spin up and electrons of spin down. So we form like Cooper pairs like that. Maybe you've learned about it in your graduate courses. And oftentimes, this Cooper pair break. Cooper pairs break when you heat them up for obvious reasons. But using the similar idea to what I've shown you for the lattice gas or the quantum field theory model, you can arrange a situation where the Cooper pair condensation has much higher entropy than breaking the Cooper pairs. So using the same exact idea, like the condensation of psi leads to many more entropically available states than without the condensation. So we just cooked up a simple modification of BCS theory, where you can show by solving the gap equation that Cooper pairs exist forever, and it's just always superconducting. And I mean, it's quite miraculous that it's possible. If it's possible in real life, then we can bring electricity from China for free. That would be fantastic, but okay, we'll see. Okay, I have like 5 minutes for if there are more questions about the ideas or more details about anything, I can try in the last 5 minutes. Okay.
One question maybe. Now you've shown us these two examples. Can you identify structurally what's the key ingredient that showed these behaviors? Like one was the classical example, one was the quantum example.
It's a good question. You see that there is something common in both examples, which is that why is the system ordered at high temperatures? It's ordered because ordering some subset of the degrees of freedom opens up many possibilities for the rest. So it's actually beneficial for the system to be in an ordered state from just a combinatorial point of view.
So from this point of view, there could be like, there's good reasons that these are not the only two examples you can come up with, but there's...
Now you can ask, can this mechanism be realized in nature, that ordered states have a combinatorially higher weight than non-ordered states? Maybe I'll say for 1 minute now, we have identified two examples in nature which seem to have this property, but at least in a small window of temperatures. So I'll tell you about these two examples to show you that this may not be science fiction. This may not be just toy models. So one example is helium-3. Helium-3 is a famous superfluid at low temperatures. It's a liquid phase. So if you look at it depends on the pressure. I'm not going to show you the full phase diagram. It's very complicated. But I'm just going to take some slice through some interesting point in pressure, which I'm not going to tell you what it is. I don't remember. So at very low temperatures, like microkelvin, it's a fluid. It's actually a superfluid, but just think about it as a fluid. There is a small window. It's a very small window in temperature. I think it's a few microkelvins, where it becomes a solid before becoming a fluid again. This small window in energy is called the Pomeranchuk window. It was first discovered by this person from the Pomeron. Maybe it's the same person from the Pomeron. And we looked like under the hood, so to speak, of how can this happen? Because it's very reminiscent of the classical statistical model I showed you. And it's actually the same thing. You can see that helium-3 wants to form a crystal, Because if it forms a crystal, some vibrational modes of the molecules, of the helium atoms, suddenly open up. And it's a purely entropic effect. So this is one example that seems to behave like what I told you for a small, of course it doesn't be, of course in the example I showed you the solid continued forever, but in this example it's just a small intermediate phase. That's another example which is easier to buy if you want to have one of those materials at home. It's called Rochelle salt. It's a, well, I don't know if I'm allowed to say it here, but you can buy it on Amazon. Maybe many grandmothers would know it. It's a laxative. So it has an interesting crystal phase at room temperature with some. It's a very nice ordered crystal. But if you heat it up a little bit, it enters a new crystal phase. Let's call it crystal prime, which is more ordered than this crystal phase. So this crystal, I think, has Z3, and this is Z6, if I'm remembering correctly. You're entering a more ordered crystalline phase. And you can ask, how is it possible that the solid becomes even more ordered as you heat it up? And the reason, if you look under the hood, it's exactly the same thing. It's just that in this little window, many new vibrational modes of the molecule open up, and they increase the entropy for a small domain in energy. So I think this shows that this mechanism is possible in nature. And yeah, we'll see if it can be applied for superconductivity or some of these things, superfluidity, something. Yeah. Any other? Yeah.
Perhaps we will come to it later, but as far as ADS-CFT is concerned, when you have model of this kind, which is essentially a vector model, the bulk dual would be some higher spin theory.
Yeah.
So do you have some examples with adjoint-like fields where the bulk dual is more like Einstein gravity?
Yeah, so the connection with ADS-CFT is not understood yet. So this would say that there is hair, but as you said, this is not a gauge, this is not a model that's holographic in nature. It may be some Vasiliev theory or something.
Yes.
So if you ask me, are there actual holographic examples which do that? I think the question is open. There is a paper from recently by Alex Bushel, who studied just the low energy supergravity, thinking about it as an effective field theory. And I think the claim in that paper was that it is possible to have hairy black holes, hairy large black holes, but he didn't find a microscopic theory that does that.
Okay. Thank you.
So yeah, the connection with the no-hair theorem is not settled. Okay.
If we do find a holographic example, then what would be the equivalence of the statement that ordered states have open up more possibilities? What would be the equivalent statement on the pulse?
It would mean that the hair of the black hole increases its entropy. Yeah, like there would be the usual entropy of the black hole, but somehow the hairy black hole has more entropy. I don't actually know how is it supposed to work. I don't understand exactly how it's supposed to work.
Thank you.
Okay.
I think this example in nature is very interesting, but it
Which examples?
Like both of them, but so what would the explanation be in like the fact that it's only a window and not actually going on infinitely? Does it mean that maybe the effective physical description that it has will somehow be weirdly temperature dependent in such a way
Yeah, but it is. It is because the vibrational modes of the molecules is a complicated thing, and you open up new modes as you heat it up. Yeah, I mean, the examples that I gave you are idealized, obviously. I think maybe the statistical mechanics examples that I gave first looks very natural, but, you know, is it going to be realized in nature on the spot? I don't know. We'll have to wait and see.
But so, like, very ideally, I guess the whole point here is that these actions are very fixed, but if we were to give a description of this stuff, ideally in, like, the thermal Euclidean formulation, we would have some Euclidean time dependence maybe of the Lagrangian?
I think it's just that, you know, to write an actual Hamiltonian for helium-3 is not a practical thing to do. You can include some modes, but nobody knows the full dispersion relation of every single mode. So that's why this description is like a little bit intermittent. It exists for a small time, for a small energy window, and that's it.
So we can say that probably more vibrational modes of the
Yeah.
disordered crystal
Exactly.
open
Yeah.
up like
Yeah,
at
once
higher
you
temperatures.
go higher, suddenly the solid is not favored anymore because this additional entropy that it gained from vibrational modes is now lower than the entropy in some fluid modes that you didn't even know existed before, because the number of fluid modes also grows. Right?
Yes, so there's this fine-tuning thing here that
Yeah,
happens.
the models that I gave you are idealized in that they have a fixed Hamiltonian with like a fixed number of fields. But it's like any toy model in physics, right? We try to isolate the important ingredients and see what they do.
Okay, thank you.
I have two questions. One is that are all examples theoretical or experimental so far about discrete symmetries? And second is, can I imagine that line in the phase diagram to turn around as you go to higher temperature?
Okay. Turn around, I'm not sure. I think it violates conformal symmetry because the diagram, usually the diagram has a scaling symmetry. Like if this is a second order transition, the diagram has to have a scaling symmetry where you maybe change the coupling and increase the temperature at the same time, some kind of scale symmetry. So usually these lines follow a simple exponent. It's related to the one of the critical exponents. So I expect these lines not to really turn around. As to continuous symmetries, I think it's an open problem. Up to date, nobody has ever found a quantum field theory that breaks a continuous symmetry spontaneously at high temperatures. There were attempts. There are some papers of Sumyadeep I've seen, and Choi, and Nakayama maybe. There were attempts, but none of them succeeded yet. So we don't have an example of a superfluid at high temperatures in quantum field theory. We have some lattice examples, but not a quantum field theory example. Okay? So it's still an open problem.
Sorry, but so if you take your model and you put just tube size, you would get some...
You mean like if I make psi a complex field or something, let's say, to break a continuous symmetry?
Maybe, yes.
That doesn't work then. Yeah, it turns out then the VEV of psi goes to 0 at high temperatures, and that's it. Yeah, it's I have not been able to find an example with a continuous symmetry.
More of a curiosity than a specific question. So I was just looking at the phase diagram for helium-3. It seems curious that exactly at the pressure window that you're talking about where a solid forms, almost exactly in that pressure window, probably exactly in that pressure window, a new liquid phase also forms. Is this something that you can understand?
This one?
Yeah.
No, that's the non-superfluid. That's what's called normal liquid.
No. I was talking below the solid. So there's the normal liquid above the solid, and then there's the solid, and then below the solid there's another normal liquid, and then below that normal liquid there seems to be another liquid phase, exactly in that pressure window.
You checked on Wikipedia or something?
I'm just looking it up.
No, I don't remember.
Seems interesting, so I was
Good. I don't remember. Yeah, actually the phase diagram is very complicated. I don't remember it. I think we need to finish. We can chat more tomorrow.